Hello friends, this video on class 10 chemistry revision is brought to you by examfear.com. No more fear from exam. So first of all, let us have a quick look at all the chapters of chemistry that we have in class 10th. So these are the chapters that we have: carbon and its compounds, periodic classification of elements, acids, bases and salts, chemical reactions and equations, and metals and non-metals. Now if we look at their priority, that is, how many questions can you expect from all of these chapters in your board exams? So based on that, the priority level for carbon and its compounds is high. So you really need to focus a lot on this chapter because you can expect 3 to 5 questions from this chapter. Similarly, for periodic classification of elements and acids, bases and salts, these two are medium priority chapters and you can expect 2 to 3 questions from these chapters. And finally, chemical reactions and equations and metals and non-metals, these are low priority chapters. Now when I say low priority, that's because you directly do not get many questions from these chapters. Having said that, chemical reactions and equations is like the basic of all the other chapters. So it's like the basis. So you always should know how to balance equations. You should always know how to write chemical equations. So that way this chapter is very important. But from the question perspective in exams, you can expect 1 to 2 questions from each of these chapters. Now overall, you would have around 8 to 10 questions from chemistry in your science board exam paper, right? So out of those 8 to 10 questions, these would be the priority of the various chapters. So we will start with the high priority chapter first and then gradually move towards the low priority chapters. So let's get started with carbon and its compounds. So what are the topics that we are primarily going to cover now? Please remember that this video is only for revision or recap purpose. So I am not going to discuss each and every topic in detail. So if you want to watch a detailed video, you can always go to examfear.com, class 10th chemistry, and have a look at all of these chapters in detail. So to recap carbon and its compounds, we will quickly discuss hydrocarbons, electron dot structure, isomers, homologous series, ethanol, ethanoic acid, soap and detergent. So these are some of the topics that we'll quickly touch upon. Now, first of all, what is so special about carbon? Why do we always talk about carbon compounds? Now, that's because carbon has the ability to form covalent bond. And why does it form covalent bond? Covalent bond is all about sharing electrons with other atoms. Now, that happens because carbon has 4 electrons in the valence shell. Valence shell is the outermost shell. So, if you look at the electronic configuration of carbon, so it has an atomic number of 6. So atomic number of carbon is 6, and if you write it electronic configuration, it is 2 in the innermost shell and 4 in the outermost shell, that is valence shell. Now these 4 electrons are there, so carbon needs 4 more electrons to be in the stable configuration. And how does it acquire those 4 more electrons? By sharing of electrons, and that's why it forms covalent bond. It also has the ability to self-combine to form long chain, and this property of carbon is known as catenation. And because of this, we see a variety of carbon compounds. Not only that, we actually see different forms of carbon also. For example, diamond and graphite are 2 wonderful examples. Now, graphite, which you see in the lead of pencils, a diamond, I'm sure all of you already know about it. And if you look at their structures, they are very much different. In graphite, you have the layered structure with weak hydrogen bonds holding the layers. And in diamond, you have a tetrahedral structure like this. So these are some, very different forms of carbon. And because of the catenation property and its tetravalence, carbon is special and we have so many carbon compounds. Now let's quickly get started with the electron dot structure of covalent compounds. Now we'll quickly discuss the steps. The first thing that you need to do is write the electronic configuration of all the atoms which are present in the molecule. Now, for example, let's say that we want to write the electron dot structure of H2O, that is water. So what are the atoms present here? 2 hydrogen atoms and 1 oxygen atoms. So we will write the electronic configuration of all of these. So hydrogen's electronic configuration is, it has only atomic number 1. Oxygen has atomic number 8. So if you write electronic configuration, it would be 2, 6. So 2 in the innermost shell and 6 in the valence shell. So number of valence electrons is 6. And hydrogen, again, number of valence electrons would be 1. Now, if we just represent the valence electrons like this, So identify how many electrons are needed by each atom to attain noble gas configuration, right? So how many electrons do you think each of these would need to attain noble gas configuration? So obviously oxygen would need 2 more electrons, because right now it has 6 in the outermost shell. It needs 2 more to become 8. Now hydrogen has only 1, so it needs 1 more to become 2, because the noble gas configuration is either you have 8 electrons in the outermost shell or you have 2 electrons, because 2 is like for helium, correct? So one of these has to happen. Now share the electrons between atoms in such a way that all the atoms in the molecule have noble gas configuration. So what we do, this 1 electron of oxygen and this 1 electron of hydrogen, they get shared. So now when hydrogen has to count the number of valence electron, it counts the electron of oxygen as well. Similarly, when oxygen has to count its valence electron, it counts the electron of hydrogen as well. So basically they are sharing these electrons. So now hydrogen has 2, oxygen has 8, hydrogen again has 2. So all the atoms have the noble gas configuration. So keep in mind that the shared electrons are counted in the valence shell of both the atoms sharing it. And this type of bond is called a covalent bond. Right? So if you have to draw the electron dot structure, this is how you draw it. So there's no need to draw the bond, but basically you have to show with dots the electrons. So that's how we draw electron dot structure. So let's talk about carbon compounds. Obviously, compounds of carbon with covalent bond, they are called carbon compounds or organic compounds. For example, CH4, C2H6. So CH4 is methane, C2H6 is ethane. So these are all carbon compounds because they contain carbon. More than 5 million organic compounds exist, and that's a really, really huge number. And why so many compounds exist? That is primarily because of catenation. That is the property of carbon atoms to self-link. That is, you see here, right? So many carbons are kind of getting linearly linked to each other. Sometimes they also form branched chains. Sometimes they form cyclic chains. So carbon has the ability to combine with itself over and again, and that's how we get so many combination of carbon bonding, and as a result we get so many organic compounds. Not only that, tetravalence of carbon, that means carbon has 4 electrons in its valence shell. So it has a valency of 4. So it can bond with 4 other atoms of carbon or atoms of other monovalent element. For example, let's say, let's draw this. Let's take this example. So here, if you see, carbon has 4 electrons in the outermost shell. Now, this 4 electron can actually combine with 4 other atoms of carbon, or for so that is one possibility. Like this, let's say if this is carbon with 4 electrons, one possibility is it can combine with 4 other atoms of carbon. Another possibility is it can combine with 4 other atoms of other monovalent element. Like in this case, if you see the carbon, 3 electrons of carbon are combining with 3 electrons of another carbon to form a triple bond like this, and the remaining 1 electron is combining with hydrogen. Right? So now since it has a tetravalence, that means it has 4 electrons in the outermost shell, so it can actually combine with a lot of atoms, right? And also, due to the small size of carbon, the carbon bonds are very strong, and as a result the carbon compounds are also very stable. So that's why also we do see a lot of carbon compounds. Now we'll talk about hydrocarbons. The name itself suggests hydrocarbon means hydrogen plus carbon. So compounds made up of hydrogen and carbon only are called hydrocarbons. For example, methane, ethane. So if you look at the composition of these compounds, they have only carbon and hydrogen, nothing else. So they are hydrocarbons. Now, hydrocarbons can be of 2 types, aliphatic hydrocarbons and cyclic hydrocarbons. So obviously aliphatic means those hydrocarbons which are not cyclic. Now in aliphatic also we have 2 types, saturated and unsaturated. So saturated hydrocarbons are those which contain only single bonds, whereas unsaturated hydrocarbons are those which contains double bond or triple bond. So the hydrocarbons with single bond, they are given a name called alkanes. Like here, if you see, it has 2 carbon and 6 hydrogen, that is C2H6. It is ethane. So ethane is an example of alkane, which is a saturated hydrocarbon, because you only see single bonds here. Whereas if you look at this structure, it has 2 carbon and 4 hydrogen, but here you have a double bond. So this is ethene, and this is an example of alkene, which has double bond in it. Now if you look at this structure, here you have a triple bond, and this is C2H2 and this is ethine. So this is an example of alkyne. So these are the different types of aliphatic hydrocarbons. You see, they do not form cyclic chain. They are all linear chains. Now if we go to cyclic hydrocarbons, they are of 2 categories. One is cycloalkane. That means they are alkane in the sense they have only single bonds, but they are in the form of a circle. So that's why they are cycloalkane. Like here if you see, it has 1, 2, 3, 4, 5, 6 carbons, and it is in the form of a circle. So this is cycloalkane. The other one is arene. So what are arenes? So arenes are basically aromatic compounds. That is, they have a special aroma of themselves, and the most commonly known arene is benzene. So benzene has a speciality that it has alternately single and double bonds. So these compounds are arenes. So cycloalkane and arenes fall under the category of cyclic hydrocarbons. Okay, so now let's quickly look at each of these types. So first we'll talk about alkanes. So hydrocarbons that are bonded exclusively by single bonds like methane, ethane, propane, butane. So here you can look at their structures as well. So you see, none of them have a double bond or a triple bond. None of them is cyclic in nature. They are all linear and they are all bonded by single bonds. Similarly, you can even have bigger structures with 5 carbon, with 6 carbon, 10 carbon, even 12 carbon. And the general formula of alkane is CnH2n plus 2. So that means if the value of N is equal to 3, in that case the compound would be C3H2 into 3, 6 plus 2, 8, C3H8. So C3H8 is propane. So if you look at this structure, you have 3 carbon and you have 8 hydrogen, right? So this is the general formula of alkane. So if the value of N is 20, in that case it would be C20, H2 into 20 is 40 plus 2, 42. So this would be C20H42. So that's the general formula of alkanes. And alkanes are chemically unreactive. As such, they do not react with any other element. Now, when you talk about alkenes, that is, they are hydrocarbons which are bonded exclusively by a double bond like C2H4, C3H6, C4H8. So this is ethene, propene and butene. So here if you see, you have 2 carbons but they are joined by a double bond. Here you have 3 carbons and you have 1 double bond. And the same is true here as well. So in this case also you can have bigger structures like this. And the general formula for alkene is CnH2n. So if the value of N is equal to 3, in this case the alkene would be C3H6, and that is propene. So if you look at this structure, you have 3 carbon and you have 6 hydrogen. They are chemically reactive, so they are not like alkanes. So they have a tendency to react with other elements or compounds. Finally, alkynes, here you have triple bond. So these are all examples of alkynes. Right now, you must be thinking that we are giving some fancy names to them like ethene, methane, butene. So how do we get those names? So very quickly, we will also talk about the names. Now here again, the general formula for alkynes would be CnH2n minus 2. And they are also chemically reactive. So basically alkanes are unreactive, but alkenes and alkynes are reactive. So let's quickly see the steps to write electron dot structure of hydrocarbons. So in this case also we have to write the electronic configuration of all atoms present in the molecule. So let's say we talk about ethane. So first we have to write electronic configuration of all the atoms present in the molecule. So what is ethane? Ethane is basically C2H6, right? So for carbon, if we write the electronic configuration, it is 2,4 for carbon, right? And for hydrogen, it is 1. So carbon has 4 electrons in its outermost shell, and here we have 2 carbon. So 2 carbon with 4 electrons in the outermost shell, and here we also have 6 hydrogen, and all these hydrogen will have 1 electron in the outermost shell. Next step is find how many electrons are needed by each to attain noble gas configuration. So carbon needs 2 more electron and hydrogen needs 1 more electron. First complete the noble gas configuration of all the hydrogen atom by bonding each hydrogen atom with a carbon atom by a single bond. Okay, so how many hydrogen we have? We have 6 hydrogen. So let's say this is 1 hydrogen, this is another hydrogen, this is yet another hydrogen. Similarly, here also you have 1 hydrogen, 1 hydrogen and 1 hydrogen. So in this fashion we have put all the 6 hydrogens here, and all the 6 hydrogens noble gas configuration is fulfilled. Now the remaining valency of each carbon is completed by carbon-carbon single, double or triple bond. So now you see these 2 carbon, they are left with 1 electron. So we can form only a single bond. So in this fashion we can form the structure of ethane. So we have to note that the shared electrons are counted in valence shell of both the atoms sharing it. So that's quite obvious. Now in a similar way, if we have to write the electron dot structure for ethene, so in ethene we have C2H4. So here again for carbon we have 4 electrons in the outermost shell, but in this case we have 4 hydrogen, 1, 2, 3 and 4. So these 4 hydrogen will form a single bond and complete their noble gas configuration. So now we see that with carbon we have 2 electrons left. So these 2 electrons will form 1 bond, and these 2 electrons will also form 1 bond. So basically there will be a double bond between carbon, and then we have these 4 hydrogen joined by single bond. So in this fashion we would draw the electron dot structure. Similarly, if it is about ethane, so in case of ethane we would see that there is a carbon-carbon triple bond, and then you have 2 hydrogens connected by a single bond. In a similar fashion, you can also look at the structure of cyclohexane. So here also if you see, so carbon will have 4 electrons in the outermost shell, and then these will either combine with other carbons or they are going to combine with hydrogen. So in fact you can try out the cyclohexane electron dot structure yourself. Okay, now let's quickly talk about the IUPAC nomenclature for hydrocarbons. Now these are the 2 tables that you need to remember in order to name any hydrocarbon. Now, depending upon how many carbon atoms are present, we give a keyword. So, if there is 1 carbon atom, we call it meth. If it is 2 carbon atom, it is eth. 3 prop, 4 but, 5 pent, 6 hex, 7 hept, 8 oct, 9 non and 10 dec. So, these are the keywords that we give. And now depending upon whether it is single bond, double bond or triple bond, we give the keyword ane, ene or ine. Let's take this example. So let's say this structure is methane. Why? We have 1 carbon atom. So 1 carbon atom means meth. And we have only single bonds. That means ane. So meth plus ane, it gives methane. Similarly, if you look at this structure, you have 2 carbon atoms. So it is eth. And you have only single bond, so it is N, so it is ethane. Looking at this one, you have 1, 2, 3, 4, 5 carbon atoms, so it is pent. And you have a triple bond, so it is ine, so this is pentyne. So it's pretty simple, right? So just depending upon the number of carbon atoms and the type of bonds which are present in the compound, you can name the hydrocarbon. Let's now talk about isomers. Now, in organic chemistry, 1 molecular formula can represent more than 1 compound. Now, that is very much possible that you have same formula, but the structures are different, so they represent 2 different compounds. So, organic compounds having the same molecular formula but different structures, they are called isomers. Iso means similar. So, here both of them have similar formula. That's why they are called isomers. So isomerism is possible only with hydrocarbons having more than 4 carbon atoms. Now why is that so? That's because for hydrocarbons with less than 4 carbon atoms, let's say that if you have 3 carbon atoms like this, now there is no way you can rearrange these carbon atoms to get a different structure. If you write it like this, it is the same thing, right? So this was also linear, this is also linear, right? Or if you write it like this, So that is also the same thing, because there is no way you can rearrange it to form a different structure. But that is not the case when you have a hydrocarbon with 4 carbon atoms or more. For example, if you have 4 carbon atoms like this, you can very well write it as CCCC. So now these two are different. This is a linear one, but this is a branched one. So their IUPAC names would also be different. So basically now you get 2 different structures, but your formula still remains the same. So you can get isomers only with hydrocarbons having more than 4 carbon atoms. So here if you look at these structures, so you would see that for all these structures, so you actually see 4 structures here, and all of these structures have the same molecular formula, that is C6H12. So all of these has 6 carbon atoms and 12 hydrogen atoms, but they are all structurally different. So this is an example of isomerism. Now it has also been observed that for a hydrocarbon with 4 carbon atoms, you get 2 isomers. For a hydrocarbon with 5 carbon atoms, you get 3 isomers. So basically, as the number of carbon atoms in the hydrocarbon increases, the possibility or the number of rearrangement also increases, and therefore you get more number of isomers. So now comes the homologous series. And what's that? It is a series, or it is a group of organic compounds having similar structure and similar chemical properties in which the successive compounds differ by CH2 group. So it is like a series where you have many compounds and all of them have similar structure, they have similar chemical properties, and molecular formula wise they all differ from the previous one by a CH2 group. So this series is an example of homologous series. So if you see methane and ethane, the difference between these two is CH2. So if you add one C and one H2 to this, you get C2H6. Similarly, if you add CH2 to this, you get C3H8. You add CH2 to this, you get C4H10. So it is a homologous series, and also all of these hydrocarbons like methane, ethane, propane, butane, they have similar structure. They also have similar chemical properties. Similarly, all the alkenes, they again form a homologous series. Similarly, all the alkynes also form a homologous series. And again, for all of these series, you would see that the difference in the molecular formula between two successive compounds is always CH2. Now the question is, why do we study homologous series? Now that is because they all have similar chemical characteristics. They also show a gradual change in their physical properties with increase in molecular mass. So that kind of helps us to predict the properties of various hydrocarbons. They have a general formula to describe difference in molecular mass of any two adjacent homologs is 14. That's because the difference is CH2. So carbon has atomic mass 12 and hydrogen has atomic mass 1. And here you have 2 hydrogens. So it is basically 12 plus 1 plus 1. That is 14. Any two adjacent homologs differ by 1 carbon and 2 hydrogen atom, yes, and they have same functional group and they have the same method of preparation, they have similar structural formula, they have same nature of element. So because of so many similarities, we find it very much convenient to study the homologous series. So if you study the homologous series, you get a lot of information about all the members of that homologous series. Now, the next important concept is functional group. So what is functional group? Functional group, as we learned that a saturated hydrocarbon, that is an alkane, is unreactive as such, but if we introduce other atom or group of atoms to it, it becomes reactive. So this other atom or group of atoms is called functional group. So let us take this example. So let's say if we add halo group to an alkane, so what do we get? We get haloalkane, something like this. Halo group would be like any halogen added to an alkane, like chlorine, bromine. So they are all halogens. So in this case, if you look at its general formula, it is Rx, where R is the alkyl group, which is derived from the alkane, and X is the halo group. So some of the examples of haloalkanes would be chloromethane, chlorobromine, and chloromethane, bromoethane. For example, CH3Cl, this is chloromethane. Similarly, C2H5Br, this is bromoethane. So these are examples of haloalkanes. Now these becomes reactive. As I said that normally alkane is unreactive, but when you add another group to it, it becomes reactive. So that another group in this case is the halo group. Similarly, another functional group could be alcohol group. So alcohol is basically OH. So the general formula is ROH. So when one hydrogen in an alkane is replaced by a hydroxyl group, so this OH group is called the hydroxyl group, we get alcohol. So some of the examples could be CH3OH, that is methyl alcohol or methanol. Similarly, C2H5OH, that is ethyl alcohol or ethanol, right? So this methanol, ethanol, propanol, they also form a homologous series, right? Then the third group could be aldehyde group. So in aldehyde group, we have CHO at the end. R is alkyl group in all the cases, correct? So in aldehyde group, some of the examples could be HCHO, that is methane aldehyde, or the common name is formaldehyde. So this is also known as methanol. Now please remember, how do we name these? For alcohol, we add OL, that is all. So we call this methanol. And for aldehyde, we add L. So it is methanol. So methanol is HCHO. Methanol is CH3OH. Correct? Similarly, if you have CH3CHO, so this is ethanol. So you have two carbon here. So eth, and you have al because it is an aldehyde. It has an aldehyde group. Similarly, C2H5CHO. So here you have three carbons. So it is propane, and this is propanol because again you have aldehyde here. Now these methanol has a common name which is called formaldehyde. Ethanol has a common name which is called acetaldehyde, and you should know all these things. So whenever you have aldehyde group, so you should have CHO as the suffix. Next is the ketone group. Now ketone group has a speciality that it doesn't occur at the end, instead it occurs in between. So it occurs in between two alkyl groups, correct? So in case of a ketone group, let's take these examples. Let's say CH3CO CH3. So this CO is the ketone group. So it has methyl groups on both ends. So what would be the name of this compound? Here you have three carbon atoms all together. So it is propan. And since it has a ketone group, so at the end we will add a suffix ONE, propanon. So propanon shows that ONE means it has a ketone group. Similarly, if you have something like this, CH3COC2H5. So here you have a methyl group this side, ethyl group this side. So total how many carbon? 1, 2, 3 carbon. So in this case 1, 2, 3, 4. This is 2. So 4 carbon atoms. So this would be butanon. Now there is another way of naming the ketone groups. For example, you can also name it like this. For the first one, there are 2 methyl groups. So you can say dimethyl ketone. Similarly, in this case, you have 1 methyl group, 1 ethyl group. So how do you name it? Methyl ethyl ketone or ethyl methyl ketone. So basically the order will be done based on alphabet. So naming, we will name both the alkyl groups attached to the carbonyl group. This CO is called carbonyl group, and then a suffix ketone will be added. So the alkyl groups will be arranged alphabetically. So methyl, ethyl, alphabetically E comes first. So we will name it as ethyl methyl ketone. Now these namings are important because many a times you get questions related to IUPAC nomenclature or common names. So basically you should know the rules for naming different compounds. Then you have the carboxylic group. So in carboxylic group you have COOH at the end. And the presence of this carboxylic group indicates that that particular compound is an acid. So how do we name these kind of compounds? Let's take some examples for these also. Let's say if you have HCOOH. So what is this? This is, you have 1 carbon atom. So this is methanoic acid, or the common name is formic acid. Similarly, if you have CH3COOH, this is ethanoic acid, or the common name for ethanoic acid is acetic acid. So in this fashion, you can have all the carboxylic acids. Not only that, you also have alkene, alkyne groups, ether group, ester group, and amines. So we are not going to discuss about all of these in detail here, but yes, the first few we discussed because you often get questions related to these groups. Now, please remember that all organic compounds having the same functional group shows similar chemical properties, and that's why we have the concept of the homologous series, because in homologous series also all the compounds in a particular series, they share the same functional group. Now let's quickly talk about the chemical properties of carbon. So first property we talk about is combustion. So what is combustion? So whenever carbon comes in contact with oxygen, what happens? So carbon and its compounds, they burn in air to release a lot of heat energy as well as light. So carbon combines with oxygen to form CO2, heat and light. For example, methane combines with oxygen to form CO2, H2O and heat and light. Similarly, if you look at this is ethyl alcohol. It combines with oxygen to form CO2, H2O plus heat and light. So whether it is carbon or it is carbon compounds, they all combine with oxygen to give carbon dioxide, heat and light. Now let's talk about oxidation. What is oxidation? It is similar to combustion, but it is like controlled combustion. So in this case, lesser amount of heat is produced. Now, if you look at the expressions here, you would see that alcohols are converted into carboxylic acids by oxidation process. So if you look at this one, this is ethyl alcohol. Now, when it gets oxidized, it gets converted to ethanoic acid. So ethyl alcohol gets converted into ethanoic acid. Similarly, if you talk about addition reaction, in this case what happens? Unsaturated hydrocarbons, that means hydrocarbons with double or triple bonds, they combine with another substance to form a single product, and as a result we see that unsaturated hydrocarbon gets converted into saturated hydrocarbons. For example, in this case, we see that we have ethene here, which is unsaturated. It combines with hydrogen and it gives ethane, which is saturated hydrocarbon, and this reaction takes place in presence of nickel and heat. So this is an example of addition reaction because two substances are adding together to form a new substance. Then you have the bromine water test, which tells that when bromine water, which is red in color, when it combines with an unsaturated hydrocarbon, it gives a saturated hydrocarbon, and as a result of this reaction, it is seen that the bromine water is decolorized. So that means it can also be used as a test for unsaturated hydrocarbons. So if you add bromine water, which is red in color, to unsaturated hydrocarbon, then the resultant solution becomes colorless. Substitution reaction. So here we see that, let's say you have methane, when it combines with chlorine, what happens? We see that the chlorine can replace the hydrogen atom one by one, and that is why it is called substitution. That is, it is substituting the hydrogen atom. So here you see earlier there were 4 hydrogen, but now there are 3 hydrogen, and instead of the 4 hydrogen you have a chlorine atom. Now in each step one hydrogen will get substituted. Like if you again react this CH3Cl with chlorine, what would happen? One more hydrogen will get replaced with one more chlorine. Again, if you add one chlorine with this one, what happens? Again we see that one more hydrogen will get replaced with one more chlorine, so it will become CHCl3. Again, if you add a chlorine to this, we see that the last hydrogen also gets substituted with chlorine and you get CCl4. So in this fashion, we see that in this reaction, the hydrogen atom gets substituted by the chlorine at each step, and this reaction takes place in presence of sunlight. Now, in case any one of you is interested to understand each of these reactions in more detail, please feel free to check out our videos on examfear.com for class 10th chemistry. Now let's quickly discuss about ethanol and its properties because it is a very useful substance in day-to-day life. So physical properties would be it is colorless, it has a pleasant smell, burning taste, volatile, low boiling point, lighter than water, mixes with water easily in any proportion, covalent compound, neutral compound, no effect on litmus paper. So it neither turns blue litmus red nor does it turn red litmus blue. Okay, so now quickly we will see at the chemical properties. So if you look at combustion of ethanol, it combines with oxygen to give carbon dioxide, water, heat and light. Now, in case of ethanol, it catches fire very easily and starts burning. So if ethanol is kept exposed to oxygen, it has a tendency to catch fires and it releases huge amount of heat and light. Now, if you talk about combustion of the same fuel in presence of heat and alkaline KMnO4, that is potassium permanganate, it is seen that it produces acetic acid, that is CH3COOH, and in this case it reacts with nascent oxygen, which is a very good oxidizing agent. Now there are two ways combustion can take place. One is by directly combining with the atmospheric oxygen. The other is by combining with nascent oxygen, which is a very good oxidizing agent. And this reaction happens only in presence of potassium permanganate. And in that case, we get acetic acid as the product. Okay. Also, here we can see that looking at this reaction, we can also say that ethanol is a clean fuel to be used for vehicles because it releases carbon dioxide, which is a harmless gas. It doesn't release harmful gases like carbon monoxide. Okay, now alcohols react with sodium, leading to the evolution of hydrogen gas and sodium ethoxide. So if you look at its reaction, that is ethanol combining with sodium, it forms sodium ethoxide here, and hydrogen gas is also evolved as a product. Dehydration. What is dehydration? It is removal of water molecule. So if this ethyl alcohol is dehydrated in presence of concentrated H2SO4 at 170 degrees Celsius, then H2O is removed from this. That means this H2O is removed. So we are left with CH2CH2, that is ethene. So basically ethanol, ethyl alcohol can be converted to unsaturated hydrocarbon by dehydration. And finally, we have esterification. Here, ethyl alcohol combines with another acid to form ester, and this process is known as esterification. So ester, this is ester, that is we have a methyl group here, then you have the carbonyl group here, followed by ethyl group here. So this reaction happens when ethanol reacts with ethanoic acid. And what do we get as a product? This is ester. This is a sweet smelling ester which is called ethyl ethanoate. So this is ethyl ethanoate. Now this is quite an important reaction. Many a times you get questions like what is esterification, or write down the chemical equation for esterification. So esterification is basically a process of formation of esters. Then how do you form esters? By combining ethyl alcohol with ethanoic acid in presence of concentrated H2SO4. This is also popularly known as ester test. So whenever you get a sweet smelling ester getting formed, that means that one of the reactants was ethanol. Now let's talk about another commercially useful substance, that is ethanoic acid. So even before we start talking about ethanoic acid, let me quickly tell you one more thing. So out of all these chemical properties, there are a few tests which are used to identify the presence of ethanol. So one of those tests is the sodium metal test. So sodium metal tests is this one, that is alcohols react with sodium to evolve hydrogen gas and a salt, and that salt is nothing but sodium ethoxide. So this reaction is used to test ethanol. So that is one test. The other test is the ester test, as we saw that when ethanol combines with ethanoic acid, whether it is forming a sweet smelling ester or not. So that is another test for this. So these are the two tests which are used for ethanol. Now let's quickly talk about another useful substance, that is ethanoic acid, and its chemical formula is CH3COOH. Common name is acetic acid. Physical properties: colorless, sour taste, smell of vinegar, boiling point is 118 degree, and miscible with water in all proportions. That means it mixes with water in all proportions. Okay, now let's quickly talk about the chemical properties of ethanoic acid. Now since it is acidic in nature, so it turns blue litmus red. So the litmus test can be performed to identify ethanoic acid. Now again, for ethanoic acid, we have a couple of tests. Like one is the blue litmus test. The other is sodium hydrogen carbonate test. So we'll talk about that as well. Now what happens when ethanoic acid reacts with carbonates and bicarbonates or hydrogen carbonates? So they react to give a salt. carbon dioxide and water. So if you look at the reaction, this is ethanoic acid. When it combines with sodium carbonate, it gives CH3COONA, right, which is a salt, and along with that it gives out carbon dioxide and water. In a similar way, when ethanoic acid combines with sodium hydrogen carbonate or sodium bicarbonate, then also it gives out a salt, and it gives out hydrogen, it gives out water and carbon dioxide. So this is how it reacts, and this reaction is known as the sodium hydrogen carbonate test. So this is called sodium hydrogen carbonate test. That means when ethanoic acid combines with carbonates or bicarbonates, it should give out carbon dioxide gas, water and a salt. Then the next reaction is with sodium hydroxide. So ethanoic acid reacts with a base such as sodium hydroxide to give a salt and water. So here if you see, this is ethanoic acid. When it combines with sodium hydroxide, which is a base, it again gives a salt along with water, and this salt is called sodium acetate, and along with that it gives out water as well. And finally, reaction with alcohol. So ethanoic acid reacts with ethanol in presence of an acid catalyst, that is in presence of concentrated H2SO4, to give a sweet smelling ester, that is ethyl ethanoid, and this reaction is called esterification, and this is also used as a test for ethanoic acid, and it is called ester test. Right? So these tests are important. Many a times you are asked direct questions based on litmus test or sodium hydrogen carbonate test or ester test, and you should know which of these tests are performed for which substance. Okay, so now let's talk about soap. This is again a very important topic, that what is soap, how does it work. So we will just quickly discuss about the working of soap. So to tell it in brief, if you look at the structure of a soap, it has two ends. Like this is one end and this is another end. So you can say that one end of the soap is hydrophilic. That is, it tends to dissolve in water. It loves water, hydrophilic. Whereas the other end is hydrophobic. That is, it tends to stay away from water. Right? So basically what happens is, the dirt, why do we use soap? To remove dirt, and the dirt is oily in nature, and we all know that oil doesn't dissolve in water. Now this soap has the speciality that one end of the soap dissolves in water and the other end of the soap dissolves in the oil, right? So basically this end will dissolve in water, whereas this end will dissolve in oil. So that is the speciality of the soap. So what happens is, let's say if this is the soap, now when you put the soap inside the water, what's going to happen? Like let's say that there is a dirt. So let's say this is a dirt particle and these are your soap molecules. So this round shaped things, they are hydrophilic. That means they dissolve in water, but the other end, this tail end, that is hydrophobic. So the tail end will get attracted towards the oil, because they are kind of they dissolve in oil. So as a result, all the tails of the soap molecules will get attracted towards that dirt or towards that oily substance, and it will form a cluster like this, and the dirt is trapped by the soap in this fashion, and this cluster is also called micelles. Now since the other end of the soap is hydrophilic in nature, so these round ends, they are dissolved in water. So as a result, this dirt which was trapped by the soap molecule, they are taken out from the clothes. Like let's say you are washing your clothes in this water. So the dirt is taken out of the clothes, and since the other end dissolves in water, so the dirt along with these soap molecules, they get washed away with water, and that's how the dirt is removed from the clothes, and that's how a soap works. So the main thing is that soap has a hydrophilic end, hydrophobic end. Hydrophobic, they help in trapping that dirt, and the hydrophilic end, it helps to get dissolved away with the water. So as a result, the dirt gets dissolved away with the water, and that's how the dirt gets removed with water. So this is how a soap works. Now, how do we manufacture soap? That is also important, because you also get questions related to the saponification process. So soap is manufactured from animal fat or vegetable oils by heating them with sodium hydroxide solution. So fat or oil added to sodium hydroxide in presence of heat, it gives soap plus glycerol, which is an alcohol. So this process of making soap is known as saponification. So you often get questions related to saponification also. Now after this reaction, NaCl is added to the mixture to make soap come out of the solution. Right? So NaCl is nothing but your common salt. Now, similar to soap, there is something called detergent. And how is detergent different from soap? The soap is not suitable for washing in hard water, whereas detergent is suitable in washing in hard water. So that's where we use detergent as cleansing agents. So detergents are soapless soaps as they act like soap, but they do not contain sodium stearate. And that is why they are suitable with hard water as well. So therefore they do not form scum in hard water. Some of the examples of detergent are sodium and dodecyl benzene sulfonate or sodium and dodecyl sulfate. So you often also get questions about differences between soap and detergent. So this is important. So how are they different? Soap is not suitable with hard water, but detergent works fine with hard water. Soap is biodegradable, but some of the detergents are not biodegradable. Soap is weak cleansing agent and detergent is like quite strong cleansing agent. So detergent will be able to clean clothes better than the soap. So these are some of the points of differences which you should know. And that's how we end this chapter and move on to the next chapter, that is periodic classification of elements. So in this lesson, there are just a few topics that you need to understand, and if you have good clarity on these topics, then you should be able to answer most of the questions. So these topics are periodic classification of elements, quick history. So that is just for your knowledge. Then you have the modern periodic table, which you should really know well, and the trends in the modern periodic table. This is very, very important, that how the variation takes place with period, down the group, across the period. So those things are very important. Okay, so what is a periodic table? It is basically a tabular display of chemical elements organized on the basis of their atomic numbers, electronic configuration and chemical properties. Because just looking at this table, we can tell a lot of things about the particular element, whether it is a metal or non-metal, whether it has a bigger size or a smaller size, whether it has higher atomic mass or lower atomic mass, whether it has higher density, lower density, higher electron affinity, lower electron affinity. So we can actually tell a lot of things about their properties as well. So till now 118 elements are known, and day by day more and more elements are getting known. So the number is gradually increasing. Okay, so let's have a quick look at the history of periodic table, that how did we actually come to what we have today. So long back around 1789, it was Lavoisier who published a list of 33 elements, grouping them into gases, metals, non-metals and earths. So just think about it. That time he could identify only 33 elements, and today we have 118 elements. So someday someone has to start it somewhere, and then gradually it increases. So that time he didn't know much about how to organize them, but yes, he tried to group them into gases, metals, non-metals and earths. Then later, after a couple of years, in 1829, Doberner observed that some of the elements may be grouped into triads. What do we mean by triads? That is a group of 3 elements. Okay, and he observed that these group of 3 elements, they had similar properties, and that is why he called them triads. So when 3 elements of a triad are written in the order of increased atomic mass, he found that the atomic mass of the middle element was equal to the average of the atomic mass of the other 2 elements. So let's say that in a triad you have element 1, element 2 and element 3. So the mass of element 2 is equal to the average of the mass of elements 1 and 3 respectively. So that was another thing that he observed, right? And he called this law as the law of triads, right? But the problem or the limitation with his observation was that he could identify only 3 triads. However, Lavoisier had found out 33 elements. So even if you group it into 3, so in that case you should at least get some 11 triads, but he could identify only 3 triads. So therefore it was a flop show. And then again a couple of years later, in 1866, Newlands gave the Newlands law of octaves. And what was that law? So octaves means 8. So Newlands Newlands arranged the elements in the order of increasing atomic masses, he found that every eighth element had properties similar to the first. That means he found that, like, as you go on 1, 2, 3, 4, 5, 6, 7, 8, the eighth element had similar properties as that of the first element. Again, as you move on further, then again the 16th element would have similar properties with the eighth element. So basically every eighth element had properties similar to the first one. So he called this as the law of actives. But again, the limitation of Newland's law was that it was applicable only up to calcium. So calcium is like, so in a way we can say that it was only applicable till the 20th element. Okay, and then with time, again in 1869 came Mendeleev, and he arranged the elements on the basis of their fundamental property, which he thought to be atomic mass. So he arranged the elements as per their atomic mass and also on the similarity of chemical properties. So now he considered two factors, atomic mass and chemical properties, and based on these two, he was successfully able to arrange almost 63 elements, and that was really good at that point in time. So he could also predict the existence of some elements which were not known at that time. So that was again wonderful. So he not only could arrange the existing elements, he could also predict some new elements. Okay. But there were certain limitations with Mendeleev's table, and the limitations were that he could not explain the existence of isotopes. Isotopes, that is those with same atomic number but different atomic masses. And he also could not explain the position of hydrogen atoms. So because of these limitations, Mendeleev's periodic table was also not like a foolproof success. And then came the modern periodic table, like the periodic table that we study now in 1913, when Moseley showed that atomic number of an element is a more fundamental property than its atomic mass. So basically it was Moseley who gave this concept that the elements in a periodic table should be arranged on the basis of atomic number and not on the basis of atomic mass. So that was the mistake that the previous scientists were making. And that's how the modern periodic table, which was given by Moseley, came into picture. So in this periodic table, the atomic number was considered as a more fundamental property, and elements were arranged based on their atomic numbers. So the modern periodic law stated that the properties of elements are a periodic function of their atomic number. So now if you have observed the periodic table very closely, you would have seen that the elements repeat their physical and chemical properties after a periodic interval, right? And that is why we see that elements in the same row or elements in the same column, they show a lot of similarity in their properties. So elements here were arranged on the basis of their electronic configuration, and if you look at the modern periodic table, it has 18 vertical columns which are known as groups and 7 horizontal rows which are known as periods. So these are the groups, like group 1, group 2, group 3, group 4, like that. And similarly, these are the periods, period 1, period 2, period 3, period 4, and so on. So we have 18 groups and 7 periods altogether. So as I said, that the modern periodic law stated that properties of elements are a periodic function of their atomic number. And what was the basis of this law? So the basis was that when elements are arranged according to their increasing atomic numbers, the element having the same number of valence electrons occur at regular interval. Now valency denotes a lot of things. Now if the elements have same valency, then they will also have same, like, their electron affinity would be like somewhat related, their electronegativity would be somewhat related, and that's how their properties will also be same in a lot of ways. Okay, so now let's talk about the periods. So as I said that the horizontal rows are called periods. So now if you look closely, that along a period, the elements in a period, they have consecutive atomic numbers, and the number of elements in a period is fixed by maximum number of electrons which can be accommodated in various shells of atom. For example, 2, 8, 18, 18, 18, 32, and so on. So I think this is very simple to understand that, for example, hydrogen is atomic number 1, helium is atomic number 2, and both of them lie in the same period. Similarly, if you go to the second period or the third period, let's say, so here you can see the example of the third period. So here you see that sodium, it has atomic number 11, and all the elements from sodium, like sodium is 11, magnesium 12, then 13, 14, 15, 16. So in one period, all the elements, they have consecutive atomic numbers. That's one thing. The second thing is that in every period, the total number of elements, for example, in the first period, you have 2 elements. Why? Because the maximum number of electrons that can be accommodated is 2. Again, in the second period, you have 8 elements. In the third period also, you have 8 elements. In fact, this is the third period. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, right? So how many elements will be there in a period? That is determined by the maximum number of electrons that can be accommodated in that particular shell. An element in a group contain the same number of shells. So it's not basically group, we are right now talking about period. So in one period, every element will have the same number of shells. For example, if you talk about sodium, so if you look at its electronic configuration, it is 281. Right? So basically sodium will have 2 electrons in one shell and then 8 electrons in one shell and 1 electron in the valence shell. Similarly, if you look at magnesium, it would be 282. It would be 2 electron, then 8 electron and then 2 electrons. So in this case, outermost shell 1 electron, here outermost shell you'll have 2 electron. Similarly, in case of aluminium, you will have 2, 8 and 3. So here in the outermost shell, you'll have 3 electrons. So basically for all of them, you will have their 3 shells only, right? So for all the elements in a period, they have the same number of shells, but the number of electrons in the valence shell would differ. Maximum number of electrons that can be accommodated in a shell depends on the formula 2n square, where n is the number of the given shell from the nucleus. So from the nucleus, what number of shell are we talking about? For example, here, if we are talking about the third shell, so this would be, so if you are talking about a third shell from the nucleus, in that case, it would be 2 into 3 square. Right? If we are talking about the second shell from the nucleus, then it would be 2 into 2 square. So with that formula, we find out the maximum number of electrons that can be accommodated in the shell. So it is the number of valence electron which decides which will be the first and which will be the last element in a period. So if you look at this example, sodium has 1 valence electron, magnesium has 2 valence electrons, aluminium has 3 valence electrons, then silicon would have 4, phosphorus will have 5, this will have 6. So basically the smallest number of electron would be the first element in a period. The maximum number of valence electrons, in case of argon, there would be 8 electrons, 8 valence electrons. So argon is the last element in the period. So in case of period, if you actually look at the structure of period in a periodic table, we see that the first period has only 2 elements and it is called the very short period. The second period has 8 elements and it is called short period. Third element also has 8 elements and that is also called short period. So if you look at this, this is very short period. This is the first period, this is the second, this is the third. So both of these are short periods. Then you have fourth and fifth periods and both of them again have 18 elements. So these two periods are called long periods. And then finally you have sixth period which has 32 elements and it is called very long period. So depending upon the number of elements that you have in a period, the period is named very short, short, long or very long. Now let's talk about groups. So these are the vertical columns. So elements in a group do not have consecutive atomic numbers because that is not possible, right? Because we are placing the elements along the periods. So now along the groups, what would be the similarity? They all have the same number of valence electrons. For example, if you compare this, so okay, beryllium. So beryllium has atomic number 4. So basically, if you actually write its electronic configuration, it would be 2, 2. Right? So that means 2 electrons in the inner shell and 2 electrons in the outer shell. So 2 valence electrons. Now if you write the electronic configuration of magnesium, it would be 282. So here again, if you draw the structure, it would be like this. So 2, 8 and then outermost shell, it will be 2. Now if you write the configuration for calcium, it would be 2, 8, 8, 2. Right? So in this case, it will be somewhat like this. You have 2 electrons again in the outermost shell. So one thing is sure that here the number of shells are different. For beryllium, it 2 shells, magnesium 3, calcium 4, but the number of valence electrons are the same. All elements in a group have similar electronic configuration. Like as I said, if you look at their electronic configuration, they are similar, right? It is 22282, 2882, then it may be 28818, something like that. All elements in a group show similar physical and chemical properties. Now their properties will also be similar because they all have the same number of valence electrons. Therefore, a lot of the properties would be similar. Number of shells increases as we go down the group. That is clearly seen here, that as we go down, number of shells would increase. So now let's quickly talk about the position of hydrogen, because there was a lot of question with regards to the position of hydrogen in Mendeleev's periodic table. Now, hydrogen has been placed on top of group 1 because electronic configuration of hydrogen is similar to alkali metals. So, these are the alkali metals, like all the group 1 elements, they are all alkali metals. But properties of hydrogen is not similar to other alkali metals due to small size of hydrogen. Okay, so the thing is that hydrogen is placed with alkali metals. Now, even though the properties of hydrogen are not similar to alkali metals, but the electronic configuration of hydrogen is similar to that of the alkali metal. So, if you look at the electronic configuration, hydrogen has only one valence electron. All the alkali metals have one valence electron. So, electronic configuration wise it is similar, but property wise it is not similar. So, that is you can say an exception with regards to hydrogen. Now let's quickly talk about the metals and the non-metals in a periodic table. Now the elements in the periodic table can be divided into metals, non-metals, and we also have metalloids, which are like in between metals and non-metals. So metals comprise more than 78% of all known elements, and they appear on the left hand side of the periodic table. So all the grayed out elements, they are metals, and all the green elements, they are non-metals. So it is very clearly seen that non-metals are towards the right hand side and metals are towards the left hand side. And you can see a couple of elements which are like grayish in color, like these all. So these all are basically metalloids. That means they are somewhere in between metals and non-metals. Now the most important part, that is the trends in the periodic table. This is very important because you get a lot of questions from the trends in periodic table, like how the various properties changes in a periodic table. So if you look at this diagram, this gives you a very nice idea that as you move from left to right in a period, we see some variation in the atomic radius. For example, as you move from left to right, the atomic radius decreases. So here this increasing arrow shows from right to left. So as you move from elements located from left hand side to right hand side, the atomic radius would decrease. Now if you talk about ionization enthalpy, then it would increase, because if you look at this yellow arrow, as you move from left to right, ionization enthalpy is increasing. Electron gain enthalpy would also increase, and electronegativity would also increase. So all of these would increase as you move from left to right in a period, except atomic radius. Okay, now if you talk about a group, what happens along the group? Now as you move from top to bottom, as you move down the group, you see that the atomic radius increases. That is primarily because the number of shells increases as you go down the group. Now if you talk about electronegativity or ionization enthalpy or electron gain enthalpy, all of these decreases as you go down the group. Similarly, if you look at the metallic and non-metallic character, as you move towards the left of the periodic table, the metallic character increases. That is why you find most of the metals towards the left of the periodic table, whereas most of the non-metals towards the right. Now this is very, very important. You get questions like this. Maybe you are given two metals and you will be asked which has greater electron gain enthalpy. So you should be aware of their positions on the periodic table. In fact, we had created a very interesting video on how to memorize the periodic table. Even though it is not required to memorize the complete periodic table, but it always helps if you are able to, because in that case you are very sure about the position of each element on the periodic table. Okay, so with that, let's quickly discuss the merits of the modern periodic table. So since it was based on atomic number, which is a basic property, so that helped. It explains the reason for periodicity of elements, why the elements show similarity in their properties every periodic intervals of time. So that was very clearly explained with the help of electronic configuration. No anomalies in arrangements, so there was no anomalies with arrangements of any of the elements. Newly discovered elements were easily accommodated. As I told you that, with every passing year we are seeing one or two elements getting added to the periodic table, and that doesn't cause any confusion, so they get easily placed in the table. Helps us understand why elements in a group has same properties, of course, because they all have the same type of configuration and same valence electrons. Based on electronic configuration, made life simple for chemistry students and chemists. Needless to say that, because once you have a very good idea about the periodic table, you know the properties of all the elements which are existing today. Now, once you know properties of all the elements, entire chemistry becomes very easy for you. You know how each of these elements would react in a certain situation. So that's how it helps a lot for the chemistry students and chemists. Easy to remember properties of elements based on its position in periodic table. As I said, if you know its position, you can actually predict all the properties of that element. Lanthanides and actinides are placed separately at the bottom of the table because these are some of the elements which have very different properties. Okay, now you will learn about lanthanides and actinides in your higher classes. So now let's get started with the next lesson, which is acids, bases and salts. So in this chapter, we are quickly going to cover some of these topics: acids, bases, salts, acid-base indicators, reaction of acids with metals, reaction of acids and bases with metal carbonates and hydrogen carbonates, reaction with oxides, strengths of acids and bases, formation of salts, family of salts, chemicals from common salt. So again, I will just quickly go through each of these topics, but needless to say that all these topics are quite important. So let's start with acids. Acid is a solution that has excess of hydrogen ions. They are sour in taste. Some of the common acids are acetic acid, ascorbic acid, which is vitamin C, carbonic acid, which is present in the soft drinks. Now, the names are quite important, even though I am not going to talk about all of these in detail, but this is important because many times you are asked a question like this, that which acid is the stomach acid or which acid is present in the citrus fruits. So you should know the name of the acids and where are they present. Then let's come to base. So what is a base? It has excess of OH ions. So that was an old definition. Later, it was defined as a substance that accepts H plus ions. So basically, acid gives H plus ions and base accepts H plus ions. So that's how we define acid and base. So they are bitter in taste and soapy in touch. So if you look at this reaction of an acid and base, so this is hydrochloric acid, HCl, and this is sodium hydroxide, which is a base. Now when these two combine, they form a salt, which is NaCl, and water is released. So acid and base, they combine together to form salt and release water. Now there are certain bases which are soluble in water, and these water soluble bases are called alkalis. For example, sodium hydroxide, potassium hydroxide, they are water soluble bases. So NH3 is a base, that is ammonia, which doesn't dissolve in water. Now as I said that it is not necessary that all bases would dissolve in water. Only the water soluble bases are therefore given a different name called alkalis. So if you look at the reaction of ammonia, it reacts with HCl. So ammonia is a base. When it reacts with acid, it forms ammonium chloride, that is NH4Cl. Now when ammonia reacts with water, what happens? It forms ammonium ion plus hydroxide ion. Now let's talk about some of the common bases. These are names of some of the common base, like aluminium hydroxide, which is used as antacids or in deodorants, ammonium hydroxide, calcium hydroxide, magnesium hydroxide. Again, you should know the names of these bases and where are they used, because you get such questions. What is bleach? So you should know it is sodium hypochlorite. Or if you are asked what is baking soda, it is sodium bicarbonate or sodium hydrogen carbonate. Okay, now let's come to salt. So what are salts? So salts are ionic compounds that result from neutralization reaction of an acid and a base. So basically, when acid and base combine, that reaction is called neutralization reaction, and the result of this reaction is a salt. So salts are composed of positively charged ions and negatively charged ions. For example, if you look at this scenario, here you see HCl is an acid which combines with sodium hydroxide, which is a base, and it forms NaCl, which is a salt. And if you look at NaCl, it is made up of positively charged ions, that is Na plus ions, sodium plus ions and Cl minus ions. So that means we can say that it is made up of positively and negatively charged ions. So you can, if you look at this particular picture, it clarifies it further. So you can see that the H plus ion and the OH minus ion, these two combine together to form water, and the Na plus ion and the Cl minus ion, these two combine together to form NaCl. Right? So in this fashion, the neutralization reaction takes place, and as a result, salt is formed. Now, if you remember the definition of acid and base, from this you can also see that acid has a tendency to release H plus ion because it has excess of H plus ion. So that is why HCl is an acid, whereas base has a tendency to accept H plus ion. So you see, this excess of H plus ion was taken up by the base and water was formed, right? So the OH ions, they tend to accept H plus ions to form water, and that is why this is base. So you see, it is as per the definition of acid and base. Okay, now what about the color of a salt? Now salt exists in many different colors. For example, if you look at sodium chromate, it is yellow in color. If you talk about potassium dichromate, it is orange. Potassium ferricyanide is red. And similarly, you have different salts which are different in color. In fact, some of the salts like magnesium sulfate, heptahydrate is even colorless. It doesn't have a color. Now, how is this important? I mean, it's just for your information. It would be good if you know this. However, I do not really tell that, you will always get questions from the colors of salt, but still I gave it to you so that you know about it. Okay. Next is acid-base indicators. Now, it is always a challenge to find out whether a substance is acidic or basic in nature, and that is where indicators are useful. Litmus solution is a famous acid-base indicator. So, it is a purple dye which is extracted from lichen. Acids turn the blue litmus red, whereas the bases turn the red litmus blue. It is like a very famous test to find out whether a particular substance is acid or basic. Okay, red cabbage leaves. So with acid, they turn red, with base, they turn green, and with neutral substances, they turn blue. So it is again an excellent acid-base indicator. Turmeric. In acids, the yellow color of the turmeric remains yellow, but in bases, it turns red. So if you add a base like sodium hydroxide with turmeric, it would become red in color. Colored petals of some flowers such as geranium and hydrangea, that also acts as an indicator. Onions. Smell of onion diminishes in a base and it remains as it is in an acid. Vanilla essence. The odor of vanilla essence disappears when it is added to a base. The odor of vanilla essence persists when it is added to an acid. So when you add it to base, it is gone. When you add it to acid, it is retained. Phenolphthalein, it remains colorless in acids, but it turns pink with bases. So all of these are just indicators, and you should definitely know about these because you may get questions like what happens to a litmus test when you put an acid to it, or what happens, how does a phenolphthalein work? So you should know how do they indicate whether a substance is acidic or basic in nature. Finally, you have methyl orange, which turns pink in acids and becomes yellow in bases. Now, this is quite important, knowing about all the acid-base indicators. So, let us now quickly see the reaction of acids and base with metals. Now, acids react with metals to form salt and hydrogen gas. So, metals displace hydrogen from the acids and form salt and hydrogen gas. This type of reaction is called a displacement reaction. So if you look at this reaction, it shows zinc plus H2SO4. So H2SO4 is sulfuric acid, right? So this zinc, which is a metal, it displaces the hydrogen from H2SO4. So you see the hydrogen is kicked out and zinc combines with sulfate to form zinc sulfate. So this type of reaction is called displacement reaction because the metal zinc displaces the hydrogen from the acid. So that's how the reaction takes place. Bases react with some metals to form salt and hydrogen gas. However, a point to be noted is that bases do not react with all metals. So they react only with some specific metals. For example, here zinc reacts with sodium hydroxide to form sodium zincoid and hydrogen gases. evolved, right? But it will not react with all sort of metals. Okay, now how do they react with metal carbonates and hydrogen carbonates? So when we talk about that, we see that metal carbonate or bicarbonate, they react with acid to form salt, carbon dioxide plus water. For example, sodium carbonate, which is a metal carbonate, it reacts with hydrochloric acid to form sodium chloride. So you see here also, this sodium metal has kicked out the hydrogen from the acid to form sodium chloride, and water and carbon dioxide are released. Similarly, sodium bicarbonate reacts with hydrochloric acid to give sodium chloride, again hydrogen gas and carbon dioxide. So metal carbonate and bicarbonate, both of them gives carbon dioxide, water and salt. Now calcium hydroxide, it reacts with carbon dioxide. Now what happens is, now we are going to understand how do some of the bases. Now, how do we know that the gas which is evolved here is carbon dioxide? So we are telling very easily that carbon dioxide is evolved. So how do we know it is carbon dioxide? So if you pass this gas through calcium hydroxide, we see that the lime water turns milky, and that happens due to the formation of calcium carbonate. So this is basically a test to prove the presence of carbon dioxide. So with this test, we prove that carbon dioxide is released during this reaction, right? Okay, so again, a point to be noted is that bases do not react with metal carbonates and metal bicarbonates. Now these are important things from exam perspective. Many a times you are asked questions like this: what happens when sodium bicarbonate is passed through hydrochloric acid? So basically, if you know this reaction, then you will be able to answer the question. Similarly, you may be asked what happens when a base is passed through sodium bicarbonate. So you should know that bases do not react with metal carbonates and metal bicarbonates. Okay. Now the question is, how do acids and bases react with each other? So we have learned about this reaction before also, that is neutralization reaction. So acid and base always combine to form salt and water. For example, HCl plus NaOH gives you NaCl plus water. So base and acid always combines to give salt. Why it is called neutralization reaction? Because the base and the acid, they try to neutralize the acidic and basic nature of each other. Okay, now reaction with oxides. So how do these acids and bases react with metal oxides? Okay, so metal oxide reacts with acid to form salt and water, which tells us that metallic oxides are basic in nature. Because normally base reacts with acid to form salt, right? So if metal oxide is also reacting with acid to form salt, that means the metallic oxides are basic in nature. So here if you take an example, HCl plus CuO. So this HCl is dilute hydrochloric acid. When it reacts with copper oxide, which is black in color, what happens? We see that the solution turns blue in color, and this blue color is due to the formation of copper chloride, that is CuCl2, and CuCl2 is also a salt, and along with this water is released. So it is almost like a neutralization reaction where we see that a salt is formed and water is released, which tells us that copper oxide or metallic oxides are basic in nature. Okay, now let us talk about non-metal oxides. So what happens when they react with non-metal oxide? Now non-metal oxide, when they react with base, they form salt and water, which tells us that non-metallic oxides are acidic in nature. So just the reverse thing, right? So here if you look at this example, CaOH2, that is calcium hydroxide, which is a base, when it reacts with carbon dioxide, which is a non-metal oxide, because carbon is non-metal, so oxide of carbon is non-metal oxide. Okay, so CO2 is non-metal oxide. So when these two react, they form CaCO3, which is calcium carbonate, that is a salt, and water. So this is again almost like a neutralization reaction where salt is formed, water is released. So we can say that the non-metallic oxides, that is CO2 in this case, is acidic in nature. Okay. There are some amphoteric oxides as well. That is, these are those oxides which show both acidic as well as basic properties. Like here in these two examples, we saw that CO2 behaved like acidic. Again, we saw that CuO that is copper oxide, it behaves like a basic. But there are certain oxides which have both acidic as well as basic properties. They are called amphoteric oxides, and examples are oxides of zinc, oxide of aluminium. For example, look at this reaction. When HCl reacts with ZnO, that is oxide of zinc, it forms ZnCl2 plus H2O, that is a salt and water is formed. But if you see here, ZnO reacts with acid, which shows that ZnO in this case behaves like a base. However, if you look at this equation where ZnO reacts with sodium hydroxide, so sodium hydroxide is a base, there also it forms sodium zincoate, which is again a salt. This shows that in this reaction ZnO behaves like an acid. So ZnO has the property that it can behave like an acid, it can also behave like a base, and that is why these type of oxides are known as amphoteric oxides. Also, we have neutral oxides which are neither acidic nor basic. For example, carbon monoxide is one such oxide which neither behaves like an acid nor does it behave like a base. Now, what happens to an acid or base in a water solution? That is again going to be quite interesting. So, acids generates H plus ions and bases generate OH minus ions. So, let us look at this expression. Now, when an acid like HCl reacts with H2O, it forms H3O plus Cl minus. So what is this H3O plus? It is basically hydronium ion. So acid gives, now what happens is this H plus HCl gives H plus ions to the water, because right now the acid has water in the surroundings. Now these H plus ions which comes out from the acid, it combines with the water in the surrounding to form H3O plus, which is called hydronium ions. So this reaction shows that when placed in water, acids tend to generate H plus ions. Now what happens to bases? Now all bases do not dissolve in water. An alkali is a base that dissolves in water. As I have mentioned before also, that those type of bases which dissolve in water, they are called alkalis. So let us look at a reaction. For example, NaOH. In presence of water, it forms Na plus and OH minus. So you see in this case, the base tends to generate OH minus ions. So in water, acids will always tend to generate H plus ions and bases will always tend to generate OH minus ions. Now let's talk about strength of acids and base. Now there are so many acids, there are so many bases. Some of them are more acidic, some of them are less acidic. So how do we know how strong an acid is or how strong a base is? So the strength of acids and bases depends on the number of H plus ions and the OH minus ions that they are capable of producing respectively. So for that we have a parameter called pH. So what is this pH? It is defined as the negative logarithm of concentration of hydronium ions, and therefore so this is just a parameter which helps us to decide that which type of substances will have what kind of pH values. So it has been seen that the scale that measures the values are from 0 to 14. So your pH scale is from 0 to 14. Now the acids have a pH value lying between 0 to 7 and the pH value for bases lies between 7 to 14. And what about 7? Now those substances which have an exact value of 7, they are neutral substances. For example, distilled water is seen to have a pH value of 7, which shows that it is neutral. All the acids, hydrochloric acid, sulfuric acid, nitric acid, they will have their pH values less than 7. Now depending upon what value they have, we can understand which is a stronger acid and which is a weaker acid. So looking at this diagram, it tells you very clearly that lower the value of pH, more acidic the substances. Higher the value of pH, more basic the substances. Okay, now let's talk a bit more about salts. Now, how are salts formed? We have seen that salts are formed by reaction between acid and base. Now, that is not the only way to form salts. So, in the first example, we are showing a reaction between base and acid. That is the neutralization reaction, of course. But other than that, also there are other ways to form salt. For example, metal and acid. For example, a magnesium, when it combines with sulfuric acid, it forms magnesium sulfate, which is a salt. Another way could be a metal and a non-metal. For example, calcium, when it combines with chlorine, it forms calcium chloride, which is a salt. Another way could be base and an acid anhydride. For example, here NaOH is a base, and then you have Cl2, which is an acid anhydride, and you get NaClO, that is sodium hypochlorite, which is again a salt. Similarly, with an acid and a basic anhydride, just the reverse. So here you have nitric acid, and with that you combine Na2O and you get NaNO3, that is sodium nitrate, which is again a salt. So these are various ways in which salts are formed. Now the reactions are quite important because you never know, you might get a question that okay, what happens when nitric acid combines with a basic anhydride? Questions like that can be expected. Now, salts can also form if solutions of different salts are mixed, their ions recombine, and the new salt is insoluble and precipitates. This is an example of precipitation reaction where you have two solutions and in the product you get a precipitate, which is like not soluble. Like here, if you see, this is lead nitrate, which is aqueous, which is a solution. When it combines with sodium sulfate, what happens? This lead kind of displaces the sodium from this sulfate, and therefore it forms lead sulfate, which is a precipitate, which is solid in nature, and along with that you get sodium nitrate. So lead sulfate in this case is a salt which is formed. So sometimes salts are also formed by combination of solutions of different salts. So that is also one way of salt formation. Okay, now let's quickly talk about family of salts. Now there are many different categories of salts, like neutral salts, a salt that does not contain any replaceable hydrogen ions. For example, NaCl, NO2, SO4. You have acidic salts, that is, they contain hydrogen ions. Now anything that has excess hydrogen ions, they are acidic. For example, NaHCO3, that is sodium bicarbonate. Again, you have basic salts, just the opposite, that is, they have a higher proportion of OH minus, that is, they tend to accept H plus. So here you see CuCO3, CuOH whole 2. You have double salts which are formed by association of two simple salts. For example, potassium alum. So these are just the salts and I'm not getting into their detail. However, if you want to understand them in detail, as I said, you can go back to examfear.com class 10th chemistry. Mixed salts which contain one acid radical or basic radical, they are called mixed salts, like bleaching powder. Complex salts, that is, they dissociate in water to give a simple ion and a complex ion. So these are the various types of salts basically. So you should know what are they and their examples. Now they might help. Okay, now some of the chemicals that are obtained from common salt, that is NaCl. Now NaCl acts as an important raw material for various materials of daily use, such as sodium hydroxide. So when you pass NaCl with water, when you mix it with water, so basically when electricity is passed through aqueous solution of NaCl, it forms NaOH. And this process is known as chlor-alkali process. Because in this process, chlorine gas is released at the anode and hydrogen gas is released at the cathode. So chlorine is released at the anode and hydrogen is released at the cathode. Then the next thing that can be obtained is bleaching powder. So when chlorine gas produced from NaCl, it is used to manufacture bleaching powder. So when chlorine is passed through calcium hydroxide, which is a base, we get CaOCl2, which is nothing but bleaching powder. Then you have baking soda preparation. So here again you see when NaCl combines with water, carbon dioxide and ammonia, we get NH4Cl plus NaHCO3. So this sodium bicarbonate is baking soda. For preparing washing soda, that is when Na2CO3 combines with H2O, it gives Na2CO3 10H2O. So these are the various ways you can prepare different substances from NaCl, and this again is quite important because sometimes you may be asked that how do you prepare bleaching powder from NaCl? Then these reactions are going to help you. So now let's move ahead with the next lesson, which is chemical reactions and equations. Now, as I said that this is a comparatively a low priority lesson. Having said that, this is the basics of chemistry. So you should be very clear with the basics, but in exams, you do not get many direct questions from this chapter. So we will quickly discuss chemical reactions, how do we balance chemical reactions, and the types of chemical reactions. So you may get questions from the types of chemical reaction. Maybe a reaction is given and you are asked what type of reaction is this. So combination, decomposition, displacement, double displacement, and combustion. Okay, so what is a chemical reaction? So whenever a chemical change occurs, we can say that a chemical reaction has taken place. For example, think of this example. You take a magnesium ribbon, and when it burns with a dazzling white flame and it changes into a white powder, so what happens? You started with the ribbon and now you have white powder. So that means some chemical change has taken place, and this reaction is called chemical reaction. That is, magnesium combines with oxygen to form magnesium oxide. So in this reaction, the substances that undergo the change, they are called reactants. For example, here magnesium, oxygen, these are the reactants, whereas the new substance that is formed during the reaction is the product. So magnesium oxide is the product in this case. Now, another examples of chemical reaction are zinc combines with sulfuric acid to form zinc sulfate plus hydrogen. So here zinc and sulfuric acid are the reactants, whereas zinc sulfate and hydrogen are the products. Similarly, carbon dioxide plus water gives glucose plus oxygen. So here carbon dioxide and water are the reactants, glucose and oxygen are the products. Now, how do we, so they were chemical reactions. And what is chemical equation? So when instead of writing the names of the reactants and products, when we write their chemical formula, then it becomes a chemical equation. So the same three chemical reactions have been written in the form of equations. Like instead of magnesium, we write Mg, which is the symbol for magnesium. So Mg combines with O2 to give MgO. This is a chemical equation. So this one is a chemical reaction, but this is a chemical equation. Now, whenever we write a chemical equation, it is important that the equation is balanced. Now, what do we mean by a balanced chemical equation? That means the number of atoms, the number of atoms for each of these. Now let's say we are talking about compounds, right? So the total number of atoms for each element on the left hand side and the right hand side should be the same. For example, magnesium, left hand side you have one magnesium atom, on the right hand side also you have one magnesium atom. That's fine. But when you talk about oxygen, there are two on the left hand side and there is just one on the right hand side. So we need to balance it. So we multiply it by 2. The moment we multiply it by 2, your magnesium on the right hand side is 2. So you need to balance this side as well. So you multiply this also with 2. So now you see you have 2 magnesium on both sides, you have 2 oxygen on both sides. So now it is a balanced chemical equation. Similarly, if you look at the next one, so here you see that. So now let's look at the next example. So I think here the reaction is different and the equation that is written is different. So they do not match with each other. So anyways, let's write the equation for this chemical reaction. That is zinc, it combines with sulfuric acid, that is H2SO4, to give zinc sulfate plus hydrogen. So this is the chemical equation for this particular reaction, right? So now the challenge is to balance this chemical equation. Okay, so let's see. So we see that zinc is same on both sides, right? Again, if you look at hydrogen, we see that again this is also same on both sides, and if you look at sulfate, that is also same on both sides. So that means this reaction is already balanced. We do not need to do anything, so it's balanced. Now let's look at a third reaction where we see carbon monoxide, it combines with hydrogen to form CH3OH. So in this case, if you see, carbon is balanced on both sides, oxygen is also balanced on both sides, but hydrogen is not balanced. So on the left hand side there are 2 hydrogen atoms, on the right hand side there are 4. So a simple way is to multiply it by 2. So now the reaction is balanced. Similarly, if we look at the fourth reaction, that is CO2 plus H2O gives C6H12O6 plus O2. So in this case again, let's compare one by one. So for carbon, we see here we have 1 carbon, here we have 6 carbon. So one good way is to multiply it by 6. Now the moment we do that, so what happens? The oxygen also changes, right? So in this side, we have how many oxygen? We have 6 to the 12 plus 1, 13. And this side we have 6 plus 2, that is 8. So obviously the oxygen number is not balanced. What about hydrogen? This side we have 2, this side we have 12. So that means this also we can multiply it by 6. So now carbon is balanced, hydrogen is balanced. Only oxygen is left. So on left hand side we have 12 plus 6, that is 18 oxygen. On right hand side we have 6, and we can't multiply anything here because that will alter carbon or hydrogen. So here we have 6 plus 2, that is 8, and here we have 18, so we need 10 more. So for that, what we can do is we can multiply this by 6. So the moment we multiply it by 6, it becomes 6 to the 12 plus 6, that is 18. So now this equation is balanced. So balancing a chemical equation is very, very important, and I think you should practice a couple of reactions so that it becomes, easier for you. So it always needs to be remembered that the number of atoms of each element remains the same before and after a chemical reaction. So basically on both the sides, their number should be same. So let us quickly talk about the rules to balance a chemical equation. So normally we follow this rule that first of all, so it talks about the priority, that now when you have carbon, hydrogen, oxygen, sodium, which one should you balance first? So balance the polyatomic first. If you have something which has more than one atoms, so balance them first. Then balance the metals, then balance the non-metals, especially hydrogen and oxygen should be at the last. And there should be no fraction which exists in the final equation. So there should be nothing like 3 by 4 CO2 or 1 by 2 CO2, nothing like that. So it should all be in whole numbers. And most importantly, the formula should not change. For example, CH4 plus O2 gives H2O plus CO2, right? So in this case, if you have to balance this, so first focus on the polyatomic ones, let's say CH4, things like that. So here you have one carbon, here also you have one carbon. So now you are only left with hydrogen and oxygen. So in this case, you have 3 oxygen this side and 2 oxygen this side, correct? And here you have 2 hydrogen and here you have 4 hydrogen. So 4 hydrogen, so to match that, multiply it by 2. So it becomes 2 oxygen plus 2 oxygen, 4 oxygen. So this side again, multiply the oxygen by 2. So now your equation is balanced. Similarly, if you look at this expression, H2SO4 plus KOH, potassium hydroxide, gives potassium sulfate, that is K2SO4 plus H2O. So in this case, first look at the sulfate. So the sulfate is balanced on both sides. Then look at potassium. So potassium is not balanced. Here 2 and here just 1. So multiply it by 2. Right? So now let's focus on oxygen and hydrogen. So if you look at oxygen, here you have 2 oxygen. Here you just have 1. So multiply it by 2. So oxygen is also balanced. Now hydrogen, you have 4 on right hand side and on the left hand side also you have 4, 2 plus 2, right? So now the equation is balanced. So now let's talk about the types of chemical reactions. So here we will talk about combination reaction, decomposition, displacement, double displacement, combustion. So let's first talk about combination reaction. This is also known as synthesis reaction because in this reaction, 2 things combine to form a single compound. So a new compound is synthesized. That is why it is called combination or synthesis reaction. So the general form of this reaction is A plus B gives AB. So A and B, they just combine with each other. So one example is, for example, quick lime with water gives shake lime, like CaO plus H2O gives CaOH whole 2. So they all just combine together to form a new product. Similarly, all of these are examples where we see that hydrogen and oxygen, they combine together to form water. Sodium and chlorine combine together to form sodium chloride. Magnesium, oxygen combine together to form magnesium oxide. So here it is all about combination. The next type is decomposition. So here one substance decomposes to form multiple things. So like if you have something like AB, so it decomposes or it breaks down to form A and B separately. So a single compound decomposes to form 2 or more chemical species. For example, if this is water, so when water undergoes electrolysis, it forms hydrogen and oxygen. So earlier it was one compound, now it decomposed to form hydrogen and oxygen separately. Now here all these are examples of decomposition where you see H2O2 gives H2O and oxygen, CuCO3 gives CuO and CO2. So it's like breaking down of a single compound to form multiple things. Third is displacement reaction. This is important. So here what happens is, if you have a compound AB, when it combines with C, C displaces B from AB. So C kicks out B from AB and takes its position. So since C displaces B, that is why it is called displacement reaction. So an element or ion moves out of a compound into another. So let us take example. For example, when acids react with metals, like HCl reacts with Mg, magnesium, it forms a magnesium chloride plus hydrogen. So if you see this metal magnesium, it displaces hydrogen from hydrochloric acid and forms MgCl2. Correct? So this is an example of displacement reaction, and all these are also displacement reactions. So if you see iron reacts with sulfuric acid, it kicks out hydrogen from the sulfuric acid and it forms iron sulfate, and the same is true for all these reactions. Let's now talk about double displacement chemical reaction. So it is similar to displacement reaction, just that a step ahead. So in this case, what happens is, if you have AB combining with CD, so in this case B is displaced from AB, at the same time C is also displaced from CD. So two displacements take place, and this B is displaced from AB and it combines with D to form BD. Similarly, C is displaced from CD and it combines with A to form AC. Since two displacements take place, that is why it is called double displacement. Now, precipitation reactions are a good example of double displacement reaction. For example, AgNO3, which is aqueous, when it combines with NaCl, which is again aqueous, it gives AgCl, which is solid, that is a precipitate, plus NaNO3, which is again aqueous. So if you look at this example, so what do you see? You see that here, in this case, Ag was kicked out from here, and in this case, Na was kicked out from NaCl. So Ag was kicked out from AgNO3 and it combined with Cl to form AgCl. Similarly, Na was kicked out of NaCl and it combined with NO3 to form NaNO3. So two displacements takes place in this reaction, and this is a double displacement reaction. Similarly, if you look at the acid-base reaction, for example, NaOH, which is a base, when it combines with acid, that is HCl, it forms a salt, that is NaCl plus H2O. So in this case, if you see, Na is kicked out of NaOH, and H is also kicked out of HCl. So this Na is kicked out, so Na combines with Cl to form NaCl. H, which was kicked out, combines with OH to form H2O. So this is also an example of double displacement reaction. Now let's talk about the combustion chemical reaction. So combustion is very similar to burning. So when hydrocarbon combines with oxygen, it gives carbon dioxide plus water. For example, when you burn wood, carbon dioxide is produced. So that's an example of combustion reaction. So here the complete combustion of hydrocarbons in oxygen produces carbon dioxide and water as byproducts. A hydrocarbon is a compound that contains hydrogen and carbon. So these are some of the examples of combustion reaction. For example, methane is a hydrocarbon. When it combines with oxygen, it gives carbon dioxide plus water. Or if you talk about octane, which is like a bigger hydrocarbon, this also, when it combines with oxygen, gives carbon dioxide and water. You talk about propane, you talk about ethanol, or you talk about butane. All of these, they combine with oxygen to give carbon dioxide and water. So carbon dioxide and water are common byproducts for all combustion reactions. So when we talk about chemical reactions, we come across two sort of reaction. One is the reaction where heat is given out, and these reactions are called exothermic. Exo means outside, so heat is given out, that is exothermic. In certain reactions, heat is taken in, heat is absorbed, that is endothermic. So endo means inside, so when heat is taken in, that is endothermic reaction. So let us look at an example. Now when magnesium combines with water, or you can say when magnesium burns to form magnesium oxide, that is an example of endothermic reaction, because you need heat for this reaction to take place. So this is endothermic. Whereas when calcium oxide combines with carbon dioxide to form calcium carbonate, heat is released in this reaction. So this is an example of exothermic reaction. Now let's talk quickly about redox reaction. So redox, that is reduction oxidation. That's where it gets its name from, red plus ox, reduction plus oxidation. So in these type of reactions, we see reduction and oxidation both taking place. So what do we mean by reduction and oxidation? We see that there are substances which are losing oxygen, there are substances which are gaining oxygen. So a substance is said to be oxidized when it gains oxygen. The substance is said to be reduced when it loses oxygen. So basically, gain of oxygen, that means the substance is oxidized. Loss of oxygen, that means the substance is reduced. In other way, we can say that gain of hydrogen, that means the substance is reduced, whereas loss of hydrogen, that means the substance is oxidized. So I think this is an easier way to remember. Gain oxygen, oxidized; lose oxygen, reduced. So let us take so we will take an example. So oxidation is gain of oxygen or loss of hydrogen, as I said just now. Similarly, reduction is loss of oxygen or gain of hydrogen. Let us take this example. Copper, when it combines with oxygen in presence of heat, it gives copper oxide. So in this case, whether copper is getting oxidized or reduced. So here if you see, earlier it was only copper, now it is copper oxide. So copper has gained oxygen, right? So therefore in this case, copper is oxidized. Gain of oxygen is oxidation. Let's take one more example. Now copper oxide combines with hydrogen in presence of heat to form copper plus H2O. So in this case, if you look at copper, earlier it was CuO, now it is Cu. So in this case, copper has lost oxygen. So in this case, copper is reduced. However, in this case, if you look at hydrogen, earlier it was H2, now it is H2O. So hydrogen has gained oxygen. So hydrogen is oxidized in this case. So in this fashion, looking at the equation, we can say which particular element is getting oxidized and which one is getting reduced. So now we reach towards the last lesson of our syllabus, that is metals and non-metals. Again, from exam perspective, it is not very important, but yes, you often get some short questions from this chapter. So here we will primarily talk about the physical and chemical properties of metals and non-metals. So let's quickly discuss metals and non-metals. So first we talk about metals. So metals are those substances which are electropositive in nature. So what do we mean by electropositive? That is, they always have a tendency to lose electrons, and that is why now the moment they lose electrons, they become positive. So that is why they are called electropositive. Okay, now all metals except mercury exist as solids at room temperature. So let us look at some of the examples of metals like gold, silver, copper, zinc, aluminium, iron, sodium, magnesium, potassium, calcium, cobalt, nickel. So these are all examples of metals. Now, if you look at one of these examples, let's say if you talk about, say, sodium. So sodium has an atomic number 11 and its electronic configuration is 281. That is, it has one electron in the outermost shell. So sodium always has a tendency to lose this one electron. So it has a tendency to lose electron. That is why it is electropositive in nature. Similarly, if you look at magnesium, its atomic number is 12, so the configuration is 282. So magnesium tends to lose these two electrons to attain the stable configuration, and therefore magnesium is also electropositive in nature. Now let's talk about physical properties of metals. That is, metals in their pure state, they have a shining surface, and this property is called metallic luster. So if you look at most of the metals, they are quite shiny. Metals are generally hard and the hardness varies from metal to metal. Yes, absolutely. Some metals can be bitten into thin sheets, and this property is called malleability. In fact, gold and silver are the most malleable metals, and that is why you see gold sheets, silver sheets are being made. The ability of metals to be drawn into thin wires is called ductility, and again, gold is one of the most ductile metal, and that is the reason why we have so many huge variety of gold jewelry available, because you can actually put them into any desired shape. Metals are good conductors of heat, and that is why we see utensils made up of metals, because they allow heat to pass through them. Metals have very high melting and boiling point. In fact, that is one of the reason why the metal utensils, when heated, they do not melt, because they have very high melting point. In fact, tungsten is the metal which has the highest melting point, and it is used in the filament of bulb. Metals are also good conductors of electricity, and that is why wires are made up of metals. Metals are sonorous, that is, they produce a sound. Like if you remember the typical sound of the school bell, which is made up of a metal, so when you beat them hard, you get a sound which stays for quite some time. So that's the sound produced by metals. They also have high density and are very heavy. In fact, iridium is a metal which has the highest density. Okay, so these are some of the physical properties. Now let's talk about non-metals. So non-metals are those which are electronegative in nature. That is, they always have a tendency to gain electrons. So there are very few non-metals when compared to metals. In fact, when you looked at the periodic table, you saw that almost 78% of the elements in the periodic table are metals. So just in somewhere around less than 30% or around 20-25% are only non-metals. Carbon, sulfur, iodine, oxygen, hydrogen, these are examples of non-metals. However, though they are less in number, but they are abundantly present in the atmosphere. In fact, if you consider the whole earth, it's like, good amount of it is covered with water, and that's why we say that hydrogen and oxygen, they are the main constituent of ocean, because water is H2O. So hydrogen and oxygen are present in abundance in earth. The non-metals are either solids or gases, except bromine, which is a liquid. So bromine is the only non-metal which is a liquid. Other than that, all of them are either solid or gases. So non-metals are also present in a variety of places, like in water, as I said. Diamond, which is nothing but carbon, diamond, coal, graphite, these are all carbon, which is a non-metal. Again, we breathe in, we take in oxygen, we give out carbon dioxide. So oxygen, carbon dioxide, they are all made up of non-metals. The plants, they survive, that's also because of the non-metals. So the non-metals play a very critical role. So again, if you look at the physical properties of non-metals, they do not have shine, not sonorous, not malleable, not ductile, poor conductor of heat, poor conductor of electricity, soft with low density. So basically their physical properties are just the opposite to that of metals. Now there are few exceptions to metal and non-metal physical properties. For example, all metals except mercury exist as solids at room temperature, because sometime back we told that metals are always solids, but there is an exception, and that is mercury. In fact, mercury is the same liquid which is used inside the thermometer. Metals having high melting points except gallium and cesium. So we also said that metals do not melt easily because they have very high melting points. But again, we have exceptions, that is gallium and cesium. These are metals, but they have low melting points. Iodine is a non-metal, but it is lustrous, because normally metals are lustrous. Metals have a shining surface, but iodine is the only non-metal which is lustrous. Carbon is a non-metal that can exist in different forms. Each form is called an allotrope. Diamond is an allotrope of carbon, is the hardest natural substance known and has a very high melting and boiling point. Graphite, another allotrope of carbon, is a conductor of electricity. So this is again an exception, because normally we say that the metals have very high melting and boiling point. Normally we say that metals are hard. Normally we say that metals are good conductor of electricity. But carbon is one such non-metal whose forms, like diamond and graphite, they show these properties which are those similar to metals. So this is basically an exception. That doesn't mean that diamond is a metal. Diamond is still a non-metal, but it is just that it is an exception. It is a non-metal which is hard, which has a high melting and boiling point. Alkali metals like lithium, sodium, potassium, these are so soft that they can be cut with a knife. They have low densities and low melting points. Now, normally we say that metals have high densities, high melting points, but again, exceptions to that are these alkali metals, which are so soft that you can even cut them with a knife, the way you cut vegetables. Okay, so now let's get back to chemical properties of metals. Now, almost all metals combine with oxygen to form metal oxides, which are basic in nature. For example, metal plus oxygen forms metal oxide. Example, magnesium, when it combines with oxygen, it forms magnesium oxide. And now when the metal oxide combines with an acid, it forms salt. It is like a neutralization reaction, which tells us that the metal oxides are basic in nature. So metallic oxides are basic, so acids react with these oxides to form salt and water. For example, hydrochloric acid, when it combines with copper oxide, it forms CuCl2, which is salt. So this is a neutralization reaction which shows that the oxides are basic in nature. Now, all metallic oxides are insoluble except calcium, barium and group 1 metals. They don't dissolve, they react with water. So it says that metallic oxides are normally insoluble in water, but again you have exceptions, that is the group 1 metals and calcium, barium. These are the exceptions, that is they react with water. Now let's talk about reactivity of metals. Now all metals do not react with oxygen at the same rate. So different metals show different reactivities towards oxygen, and based upon the reactivity which is shown by different metals, we come up with a reactivity series so that we get to know that which metal is more reactive and which metal is less reactive. So first of all, we do this study by looking at their reactivity with oxygen. So for example, metals such as sodium and potassium, they react so vigorously that they catch fire if kept in open. Hence, to protect them and to prevent accidental fires, they are kept immersed in kerosene oil. So you see, they are so much reactive that if you keep them exposed to air, that is exposed to oxygen, they will immediately catch fire. So that they are so very reactive. So to prevent that happen, we keep it in kerosene oil so that they do not come in contact with oxygen. At ordinary temperature, surfaces of metals such as magnesium, aluminium, zinc, lead, etc. are covered with a thin layer of oxide. This protective layer prevents the metal from further oxidation. So even these metals, they get oxidized, and to prevent the oxidation, we keep a protective layer on all of these metals. Again, iron does not burn on heating, but iron filings burn vigorously when sprinkled in the flame of the burner. Now, these facts are important because sometimes you get questions like this, that why do you keep sodium or potassium immersed in kerosene oil? So these are factual based questions. Or you may be asked, why do you have a protective oxide layer on aluminium? So when you know these facts, you will be able to answer those kind of questions. Copper doesn't burn, but the hot metal is coated with a black colored layer of copper oxide. So you see, what does this show? This shows that all of these metals are reactive towards oxygen. So they tend to get oxidized, and to prevent that oxidation, some or the other measures are taken. Silver and gold do not react with oxygen even at high temperature. So they are like the least reactive metals so far. So till now, whatever we studied, we feel that silver and gold are like the least reactive. Now let us quickly look at metals reaction with water. So we see that metals react with water to form metal oxide and hydrogen. And when this metal oxide further reacts with water, it forms metal hydroxide. So that's how metals react with oxygen. Metals react with water. Now, an important point to be noted is that all metals do not react with water. Some metals are highly reactive towards water. Some metals do not react with water at all. So let us look at some of the metals. For example, potassium. It reacts with water violently, even with cold water. So even if the water is cold, it reacts with cold water, and that too violently, and it releases a lot of heat energy. Huge amount of heat energy is released. In fact, so much of heat energy is released that it can catch fire immediately. So potassium, if it is exposed to water, it can immediately catch fire. Right? So it is highly reactive. Similar is the case with sodium. So sodium also violently reacts with water to form sodium hydroxide, and so much of heat energy that it can catch fire. So these sodium and potassium, they are highly reactive. The next is calcium. So calcium also reacts with water, but it is less violent reaction. So in this case also energy is released, but not so much heat is released to catch fire. So here also calcium hydroxide is formed, but it doesn't catch fire. So it is at least less violent than that of sodium or potassium. Next is aluminium. So in case, even before that, we have magnesium. So in case of magnesium, it doesn't react with cold water actually, but it reacts with hot water. So it reacts only with hot water, which shows that magnesium is little less reactive than sodium, potassium or calcium. Now when it comes to aluminium, It doesn't react with cold water at all. It doesn't react with hot water either, but it reacts with steam. So aluminium basically reacts with steam. That means aluminium is even less reactive, and then it forms aluminium oxide, and hydrogen is also released in the process. And the same thing is true for aluminium, iron as well as zinc. So for iron also it reacts with steam. Doesn't react with cold water, doesn't react with hot water, reacts only with steam. And there are certain metals like lead, copper, silver and gold which do not react with water at all. Doesn't matter whether it is cold water, hot water or even steam, they do not react at all. So based on these reactions, we can say that the reactivity series seems somewhat like this. Sodium and potassium, they are like the most reactive. Now at least till now, we do not know whether sodium is more reactive or potassium. Then comes calcium, then magnesium, then aluminium, iron, zinc. Again, we do not know which one is more. And then at the last section comes lead, copper, silver and gold. Now, so this was our analysis only on the basis of reaction with water. So now we will look at more reactions with other substances, and based on that, we will come up with a reactivity series. So next we will see the reaction with acids. So we see that metals react with dilute acids to form salt and hydrogen, and the rate of formation of bubbles was the fastest. Now if the rate of formation is fastest, that means hydrogen is forming fast. That means the reaction is taking place fast. That means the metal is more reactive. So we see that the formation of bubbles is the fastest in case of magnesium. In fact, the order is like this: maximum in case of magnesium, then aluminium, then zinc and then iron. So this basically gives us an information about the reactivity series of these metals at least. So now earlier whatever information we had, now we have little bit more information. So now we know that okay, first is sodium or potassium, then calcium, magnesium, aluminium, zinc, iron. So this portion got clarified from the information that we received from reaction with acids. So this is how the reactivity series look like now. Right, so in this fashion the metal reactivity series was created. Now, hydrogen gas is not evolved when a metal reacts with nitric acid. Now, this is an important fact which you should know, because mostly we know that, okay, whenever a metal reacts with acid, hydrogen gas is evolved. But that doesn't happen in an exception case, and that is the case of nitric acid. Why? Because nitric acid is a very, very strong oxidizing agent, and therefore it oxidizes hydrogen produced to form water, and itself gets reduced to one of the nitrogen oxides. So, because of this reason, when metal combines with nitric acid, hydrogen is not produced, because that hydrogen gets oxidized. So that hydrogen gets oxidized to form water. So now let's look at metals reactions with salts, with solutions of other metal salts. So now we have a final reactivity series which looks somewhat like this. Now this is the reactivity series which is very, very important, because if you do not know this, you will not be able to understand the concept of displacement reactions. Now reactive metals always displace less reactive metals from their compounds in solution. So this is the most important part here. Let us take this example. So if you have a metal A which is combining with salt solution of metal B, so metal A will be able to displace the metal from the salt solution of B only if metal A is more reactive than metal B. So how do we know whether metal A is more reactive or not? Based on this reactivity series which is shown here. Let us take this example. Let's say lead combines with chloride of copper, right? So this is a solution of copper and this is lead. So if lead is more reactive than copper, in that case lead will be able to displace copper. So let us look at this series. So lead is here, copper is here. So lead is on the top compared to copper. That means lead is more reactive than copper. So therefore lead is able to displace copper from the solution and becomes lead chloride plus copper. So let's say that if you have something like this, let's say lead combining with MgCl2. So in that case, what will happen? In that case, lead will not be able to displace magnesium, because magnesium is more reactive than lead. So therefore, in this case, lead will not be able to displace magnesium. So now let's look at metal and non-metal reaction. Now when a metal and a non-metal react with each other, transfer of electrons take place from metal to non-metal. Let's look at this one. Let's say Na plus, sodium is a metal, chlorine is a non-metal. When they combine, sodium always had a tendency to lose electrons because it is electropositive in nature. Chlorine always has a tendency to gain electron because it is electronegative in nature. So as a result, the transfer of electron will happen from sodium to chlorine. The compounds which are formed in this manner is called ionic compounds, because here the bond which is formed between them is due to the loss of electrons or the gain of electrons. Here sodium is losing one electron, chlorine is gaining one electron, so they are basically not sharing the electrons. So it is like sodium is giving this one electron to chlorine and chlorine is taking that electron. So there is no sharing, it is transfer of electrons, and this type of bond is called ionic bonds, and such compounds are called ionic compounds or electrovalent compounds. So if you look at the properties of these compounds, you see that these compounds are generally solid and quite hard, because the bonds in such compounds, that is the ionic bonds, they are also quite strong force of attraction. They also have high melting and boiling points. When you talk about solubility, they are generally soluble in water, but they are insoluble in other solvents like kerosene, petrol, etc. They do not conduct electricity in the solid state, but can conduct electricity in the molten state or when dissolved in water. So these are some of the properties of ionic compounds. Sometimes you are asked questions like, what are the differences between ionic compounds and covalent compounds? So I think you know, ionic compounds, they have the ionic bonds. Covalent compounds, they happen due to sharing of electrons, and that is covalent bond. So now that we have been talking about metals, it becomes important to also talk about the extraction of metals. So where do metals exist in the earth? Okay, now the elements and the compounds which occur naturally in the earth's crust, they are called minerals, and these minerals, they have high percentage of metals present in them. Now our job is to profitably extract those metals from the minerals. Right? So that's the whole idea. Now those minerals which have very high percentage of metals, such that metals can be profitably extracted from them, they are called ores. So these are some of the terms which you should know when we are talking about extraction of metals. Minerals, what are minerals? Minerals are the naturally occurring substances which contain metals. Okay, now it may happen that you have a rock which has just 1% of gold. Just an example. Okay, that means it is very small amount of gold. So now in order to extract that small amount of gold from that huge rock, it is going to take a lot of effort. You will also have to follow a process, spend a lot of money. So it might not be profitable to do so much of extraction process just to get 1% of gold. So that means this is not going to be a profitable thing, right? So in this case, this rock is just a mineral. However, if you have a rock which has, let's say, 50% gold in it, okay, that means it has huge percentage of metal, and the metal can also be profitably extracted from it, because gold is an expensive metal, at least as far as the present economic condition is concerned. So since gold is expensive, so now when you extract gold from this, it is going to be a profitable thing. So in that case, this rock will be called as an ore. So ore is the name given to those minerals which have very high percentage of metals, such that metals can be profitably extracted from it. So they are ores. Now this entire process is what we are going to discuss in extraction of metals. Now some metals are found in the earth's crust in the free state, for example gold, silver, platinum and copper, whereas some of them are found in the form of compounds like potassium, sodium, calcium, magnesium. They are generally found in the form of compound, that is, they combine with some other element and they exist in some other form. Now moderately reactive metals, for example zinc, iron, lead, they are found in the earth's crust mainly as oxides, sulfides or carbonates. So you see, you have many different types of metals and they are existing in many different states. Some are in free state, some are in the form of oxides, some in the form of sulfides, some in the form of carbonates. So now when we have to extract metals, we need to follow a strategy. So what is going to be that strategy? Okay, so we will discuss about that. So here another important point to be noted is that ores of many metals are oxides. This is because oxygen is a very reactive element and is very abundant on the earth. So therefore what happens is, normally any metal tend to react with oxygen and form oxides, and therefore we see oxides existing at a lot of places as ores. Okay, so now we group metals into three categories for extraction. So what are the three categories? Metals of high reactivity, metals of medium reactivity, and metals of low reactivity. That means the metals which are very less reactive. So since they are less reactive, therefore they are found in the native state. For example, gold and silver. Metals with medium reactivity. So they are found in the form of compounds like zinc, iron, lead, and copper. Metals of high reactivity, they are so reactive that they are never found in the free state. They will always be found with some other compound like sodium, potassium, calcium, magnesium, and aluminium. So these are the three categories of metals, and now we will see what are the various ways that we adopt to extract these metals. So obviously, since the metals have different types of reactivity, therefore the methods used to extract these metals will also be different. So this table tells us how do we extract metals from ore. So you see, we are talking about three different processes. So for metals of low reactivity, so the metals which are of low reactivity, in that case, heating alone is enough. So what is roasting? It is strong heating in presence of excess air. So if you heat the metal, heat that ore very strongly in presence of excess air, in that case only you are able to extract the metal from the ore. For example, let me give an example. Let's say it is zinc sulfide. Let's say the ore is in the form in presence of excess of oxygen will give zinc oxide plus SO2. Right? So and then from this zinc oxide you can get the metal, and then refining of the metal is done so that it's like the last minute cleaning to get the pure metal out of it. So that is how we handle metals with low reactivity. Similarly, metals with medium reactivity, they exist either as carbonate ore or as sulfide ore. So if it exists as sulfide ore, we do roasting, that is the same thing, heating strongly in presence of excess air. Whereas if it is present in the form of carbonate ore, in that case we do a process called calcination. So that calcination means heating strongly in limited air. Roasting is heating strongly in excess air. Calcination is heating strongly in limited air. For example, zinc carbonate. When you heat it in limited air, it forms zinc oxide plus CO2. So this is an example of calcination, and this is an example of roasting. And then you get the oxide of the metal, so the metal can be reduced from there, and then the metal can be refined and purified. So that's about the metals with medium reactivity. Now when you talk about metals of high reactivity, in this case the process that we follow is electrolysis of the molten ore. So by passing electricity, we actually get the pure metal from the ore. So these are the various ways by which we extract metal from ore. So I have not discussed about each of the process in detail, but yes, I have given a quick recap. In case you want it in detail, then I think you will have to watch the detailed video of class 10th chemistry on examfear.com. Now let's quickly talk about corrosion and its prevention. So sometimes you get questions like this: what is corrosion? So have you observed that any substance which is made up of iron, when you keep it in open, exposed to air, exposed to water for a long time, what happens? It gets coated with a brown colored layer. For example, in this picture you can see that, right? So it loses its shine and it gets coated with a brown flaky substance, and that flaky substance is called rust, and this entire process is corrosion. Now for corrosion to take place, both water and air exposure are needed. So if you keep it covered somewhere such that it is not exposed to air or water, in that case it will not be it will not undergo rusting, but only when it is exposed to both air and water, corrosion will take place. However, there are various ways by which rusting can be prevented, like by painting so that the surface doesn't get exposed to air or water, by oiling, greasing, galvanizing. What is galvanizing? Coating a thin layer of zinc over iron, so that this thin layer of zinc will prevent the contact of iron with air or water. Chrome plating, anodizing, making alloys. What are alloys? They are homogeneous mixture of two or more metals, or a metal and a non-metal. So when you mix two metals, or when you mix a metal and a non-metal, in that case also the rusting can be prevented, because now you just do not have iron. For example, steel is not pure iron, right? So it is like iron combined with some other metals to form steel, and therefore steel doesn't rust. So these are some of the ways by which rusting can be prevented. To know about these methods in more detail, you can watch the detailed video. The link of that video is given in the description section. So with this, we end our crash course of class 10th chemistry. So I tried to cover all the lessons of class 10th chemistry in short. However, I have tried to focus more on the important topics so that you do not miss these important topics before your board exams. Make sure that you watch this crash course video till the end, and you also give very much importance to all the topics that we have discussed in the crash course. So I wish you guys all the